Okay. Well, this is a bit shortened, so that's okay. That's okay. That's okay. So this is the only work with my co-authors that you see here. So my talk will be about combinatorics, right? So a vertex is a vertex and nothing else. And more particularly about analytic methods in combinatorics with the aim of obtaining asymptotic counting and properties of some random graphs that I will explain in a moment. And let me see, this is advanced. Okay. So this is the starting point of our work. Okay. As I will say later, the number of planar graphs with n vertices is asymptotically given by this expression. So there is an exponential term, gamma to the n factorial, and gamma is a well-known, well-determined constant. And then there is a prefactor of n to the minus 7 over 2 and a constant. Okay. But if I take a subclass of planar graphs, they are called series parallel graphs. They are much simpler in structure. They are those graphs, for those who you may be familiar, that can be reduced to a point by series and parallel reductions, but they are really a simpler class of planar graphs. The asymptotic estimate is this with a different constant with an exponent which is minus 5 over 2. And we wanted to understand why these two exponents occur, because we had other examples that I will show of asymptotic enumeration, and our goal was to explain the appearance of these sub-exponential terms.
These numbers, gamma, they are obtained exactly, or?
Yeah, they are analytic constants that we have determined. Yeah, they are exact. But yeah, they are given as solutions of some analytic equations, but okay, this is just a rough approximation.
And they are not 1 3 times the other.
No, no, they are not. They are not. Okay. So I'm going to talk about two things. One is counting graphs, and the other is properties of random graphs. However, this is not the Ernst-Renyi model in which you draw edges independently. If I talk about a random planar graph, the probability model is a different one, as I will explain in a moment. Okay? And the kind of questions is how many planar graphs. This was the content of the previous slide. For instance, how many edges in a random planar graph? I mean, if you fix the number of vertices, the number of edges can be at most 3n. So what about how is distributed the number of edges? And then what about the size of the largest component, or 2 connected component, or 3 connected component? I will talk later, and we have answers for this. What about the degree distribution, the distribution of a vertex in a random planar graph? This is something we solved recently, but I will not have time to talk about it. And here is the probability model. So first, graphs are labeled, right? So vertices are labeled 1 to n, and two graphs are the same, even only if they have exactly the same set of edges. Of course, you can ask the same questions about isomorphism classes or unlabeled graphs. They are more difficult, and they have not been solved in the most interesting cases. And random means a uniform distribution, right? For instance, on 5 vertices, there are 2 to the 10, which is 1024 graphs. And 1023 are planar, because K5 is the only non-planar graph. And when I say a random graph on 5 vertices planar, I just pick one of them uniformly at random. They all have the same probability distribution. It's not clear how to draw them with a uniform distribution. However, very recently, Eric Fusy has generated a very efficient algorithm for sampling uniform random graphs, which is based on generating functions, which is my main tool. You can access his web page, and the code is there. You can run the algorithm, and it's very efficient, up to very large numbers, like 10,000 vertices, which is very remarkable.
And these are planar graphs, which is distinct from plane graphs.
Planar graphs, yeah, that's the main point. I mean, we don't care about the embedding. They can have many different embeddings. If you care about the embedding, then there are maps, and I will say something about maps later.
They are not connected.
No, arbitrary. Yeah, okay. Oh, how does it? Okay, so as I said, this is something we did with Omar Jimenez, my co-author. This is the number of planar graphs. The number of trees, this is a very nice closed formula that everyone in combinatorics, in enumerative combinatorics knows, if you just do the asymptotics by a Stirling estimate, you get this minus 5/2. Okay? And then when Manuel Bodisky and Hyun Khan, who is in this room, we did this series parallel or maybe outer planar case, which is even a simpler class of graphs. We got this minus 5/2 exponent. Of course, I mean, these exponential terms change, but this is the exponent which was the same. And somehow, as our terminology is that whenever we have this minus 5/2, we say tree-like. Well, tree-like because it's like trees, because trees have the same behavior, but I will say later something that they share with trees, with some structural properties that they share with trees. And this minus 7/2, we call it map-like, because in the solution of our solution on the counting of planar graphs, we had to work with maps. Maps are planar graphs with a specific embedding in the sphere, and then counting is easier, and the generating functions for maps have some properties that are somehow universal, and we believe it is correct to call it map-like.
And the maps have also -7/2, but with an even bigger gamma?
Excuse me?
The maps, the asymptotics has n to the -7/2 with a bigger gamma?
No, it's n minus 5/2, but maps are different. They are unlabeled objects. They are counted according to the number of edges, so it's a different situation.
From the root.
Sorry?
Whenever you say the critical exponent 5/2 for planar maps, it means rooted planar maps. So
Yeah, maps are rooted. It's a different world. Okay, it's a different world.
one down.
But the main point I will try to show later is that they have different structural properties with random graphs chosen uniformly at random. I mean, they are really at global structure is different. Okay. So let me start. This is the general framework we use for the analysis. So we fix a family of 3 connected graphs. We are only interested in families which are not too large. They have moderate growth so that the corresponding analytic functions, generating functions are analytic and they converge. Okay? And then the family G is the family of graphs whose 3 connected components are in T. What are the 3 connected components? And this is, I'm not very good at making pictures here, so this is why I have this slide here. So all of you know what is a connected component. So what is a 2 connected component? Well, I have here a graph which is connected, and then just it decomposes into 2 connected components along cut points. So the red points are the cut points, and these are the blocks or the 2 connected components. That's well known, and they are like a tree. They are in a tree fashion, okay? So that you have blocks and cut points, so it's a nice decomposition. Now, 3 connected components is a bit more delicate, a bit more complicated. I mean, this is due to several authors, but I think essentially many ideas come from Bill Tatt in the 60s, and you will find this in his book Connectivity in Graphs and all the papers. And the idea is I take a 2 connected graph. It is 2 connected, so it has not cut points, but it has 2 cuts, so pairs of points that separate the graph. Like for instance, these 2, they separate the graph. Okay, and then I recursively decompose on these 2 cut points, and at the end I get something which essentially are 3 connected pieces, but this is recursive. So for instance here, I have here, this is a K4, but this edge is not necessarily present. So this is another K4, but this edge has been substituted by something more complicated and so on. And this is a wheel which is attached to a K4. But there is a concept of taking a 2 connected graph and decomposing uniquely into some 3 connected pieces. But the difference is that now these 2 connected components didn't share edges. They only share vertices. But here, these 3 connected pieces like this K4 and this K4, which is still with some substitutions, they do share edges. Okay? But this is unique and this is unambiguous, so you can translate this into generating functions. So this is the family. Here are some examples.
And this would again be a tree-like decomposition?
This is tree-like, but more complicated. But essentially it's tree-like because you are recursively cutting along 2 cuts. Okay? So if I take T, the planar 3 connected graphs, the family G are all planar graphs. Somehow because a graph is planar if and only if it's 2 connected and 3 connected components are planar. If I add K5, then G is the family that do not contain K33 as a minor. Well, planar graphs are those that do not contain K33 and K5. This is a theorem of Wagner from the 30s. So it's a bit larger. On the other hand, if there are no three connected members, then G is exactly the family of series parallel graphs. I will say something about graph minors, but very, very much on the side. These are graphs that do not contain K4 as a minor. If I take T, just K4, just one three-connected graphs, then G is the family of graphs not containing the wheel. This is the wheel on 4 vertices as a minor, right? And here is a somehow not very natural example, but it could be like that. So I take T as the family of planar triangulations. So planar graphs in which every face is a triangle. This is somehow a bit artificial example, but it will show up later. And then the family of graphs is those graphs which can be done using these recursive decompositions. But at the end, for instance, you can get K4, but not the wheel, because the wheel is not a triangulation. Okay? And you can make variations on that. Okay? So we fix the family of three connected graphs. And then our approach is generating functions and what is called singularity analysis of generating functions. Okay? So the main reference for me is the book by Flageolet and Sedgwick. I usually say it's forthcoming, but it has been forthcoming for many years. But now I know that it has been sent to print. Okay? So it will be published by Cambridge University Press, if I'm not mistaken. So it should appear this year. But many of us have used Flageolet Sedgwick, his version in the web, and the main tools come from this method of doing analysis of analytic functions and their singularities.
Is it true the converse of 2 that planar plus K23 leads to no K5 minor?
No.
That one is false.
No K5 minor is much more complicated. Much more complicated. Okay? There is another structure theorem, but it is more complicated. You have to go beyond three connected components. So I fixed the generating function. Well, first of all, generating functions are exponential. Okay? So you've seen the talk by Labelle. This n factorial is because our graphs are labeled. Okay? So T and Z is the number of three connected graphs that I fixed at the beginning with n vertices and k edges.
Must be Z to the K.
Oh yeah, there is a mistake here, sorry. It must be Z to the K, yes. Excuse me. And then from this, I also have other generating functions that I call B, C. Well, you see, B will be the two connected members. And the mnemonics is that B is biconnected. The T is three connected. C is connected, which is consistent. G is all graphs. And then we need some two, let's say, auxiliary functions, which are corresponding to something called networks and series networks. And these generating functions are linked by functional and differential equations. Okay? I'm not going to give a technical talk. So I'm not going to go into all the details of the generating functions and how you solve them, how you do the singularity analysis. But I want you to look at the shape of the equations we get. And these are the equations. So T is three connected, B is two connected or biconnected. This is mnemonics. C is connected, G is graphs, and these two are somehow have a secondary role. And they help in the decomposition along three connected components. So the first question, you see this exponential is again an appearance of the exponential formula. This is when you glue two things, instead of gluing two things along these two cards, I can glue many things. Okay, so a set of things, and this is the exponential formula. And you must take an exponential of something which is either series or which is a three connected graph, so this is T. The subscript is derivative. And we have seen this morning that when you do subscript, you have an edge which is rooted. So there is an edge which is distinguished. And then on the right, we have a substitution. And the variable z has been substituted by something more complicated. Is this substitution here? So these edges become substituted by something else. Okay, so this is one of the equations.
Well,
So,
if you're doing two or more things, why do not have exponential minus versus series terms?
excuse me?
If you are gluing at least two objects, why don't you have exponential to something minus 1 minus x?
Well, no, not necessarily. I mean, not necessarily. It could be just one thing. You don't necessarily glue. I mean, just root at an edge, and at this edge there is only one thing. Okay? Or maybe there is nothing, and this is the first term of the exponential. The second one is that some of these things are called series. Series is that you put one and then the other and the other and the other and the other. And then a serious thing is something which is not serious, so d minus s, times something which is arbitrary. So more or less this is. And if you eliminate the s from these two equations, you get this equation. Okay, let's have a look at this equation. Let's have a look. I just eliminate s, and I take logarithms. Okay? So this is t that I assume that I know from the beginning, because I need to know not only which are the three connected members, but to be able to count them in order to have in my hands the generating function for the three connected members. For instance, for planar graphs, these would correspond essentially to three connected maps. And the reason is the beauty of this fact is that a planar graph, when it is three connected, there is a unique way of drawing it in the sphere. This is Whitney's theorem. So at the three connected level, there is an equivalence between planar graphs and planar maps. And this is the starting point. Okay? This was noticed in a paper in some 5 years ago by Bender, Gao, and Nick Wormel, and this was the starting of everything. Okay? This realizing that you can use maps instead of, and the generating function for three connected maps is known from the 60s. It's some algebraic function which is explicit and it's well known. But I don't want to give all the details. So assuming t is known, somehow d is given through this functional equation, and we can analyze d. Now come the second two equations. Essentially what this is saying that this is a two-connected graph rooted at an edge. This is the derivative with respect to y, is given by this d. So this is a relation between the b and d. The only problem is that we have b differentiated with respect to y. So if you want b exactly, you have to integrate with respect to y. And this integration at the algebraic level, so this is a formal integration, is not always easy. Okay? So sometimes you have to do a lot of algebraic work in order to get b, not derivative, but really the b you are interested in. And the second two equations are also they are very classical. So you know, now I differentiate with respect to x. This means that I am rooting at a vertex, and this has appeared in several talks today. I multiply x because I want this root to have a label. So these are rooted connected graphs. And this is again the exponential formula. This is the root, and this is the two connected components to which it belongs, and then you do a substitution. So I fix this vertex here, for instance, here. This is in two connected components, so these are the b's. But again, in every two connected component, I have to do recursively. And so this is equation linking b and c. But there are also derivatives. And the final equation is just the exponential formula. So graphs are exponential or connected graphs. And y is marking the number of edges. And this is additive because, I mean, connected components and two connected components, they do not share edges. So this works very well. So we are given t. I assume that the generating function t is known. And at the end, I want to know enough about g in order to get the asymptotic number of some properties of random graphs. So you have to go through a series of steps. And somehow the difficulty means depends on the complexity of the function t. So for planar graphs, t is quite complex, and this makes these different steps a bit hard. In the case where t is 0, this is series parallel. There are no three connected members, so t is 0. And then in this case, it's a bit smoother, but still, at some points, you have to do some work, right?
Quick question. So do you use Whitney's theorem to derive one of these?
No, Whitney's theorem is if you want to determine the generating function, for instance, for three connected planar graphs, I say it's enough to work with maps. And there is a rich theory of counting maps, which I understand has deep connections with physics, although this is not my topic, really, I must say. And for instance, the counting of three connected maps was known from the 60s. So this is built at, and here's a school, and several of the results we need were already there. Right? Now comes the analysis. The analysis means that we are interested at generating functions at the dominant singularities. Dominant singularities means the singularity of the smallest modulus. And since the coefficients are non-negative real numbers, the dominant singularity is always achieved at a real number. So our assumption is that this t function has some singular development around the dominant singularity, which is of the fractional type. I mean, this is typically what you get for algebraic functions. This is called Newton-Puiseux expansions. So you get expansions near the singularity in fractional powers. And all our functions are of this type. So we assume that we have such a singular behavior. And this alpha here is what we call the singular type. And the singular type is later when you translate the behavior of a function near the singularity to the coefficients of the Taylor expansion is what is giving this n to the minus 3 halves, minus 5 halves, minus 7 halves, and so on.
It is so automatic that alpha is constant in X.
Oh yes, yes. Imagine it is. If it is 1/2, then I'm saying it is a square root. I'm just saying it is of the square root type.
But we are working at fixed X for various X. It could be, in principle, an alpha of X.
No. I'm fixing it in this case. For technical reasons, I'm fixing X, and I'm looking at the function as a function of Z. So as a function of Z is essentially a square root of Z. Well, it's a square root of 1 minus Z over Rx, and Rx is the dominant singularity, which is a constant value. Right?
But Andrea is asking, it's not immediately obvious that at different x's you get the same singularity structure.
This is not true. Not necessary. In general.
Oh, alpha could depend on x.
Yeah, but not in this case. I mean, we are in a situation in which alpha, I mean, this is a non-movable singularities. I mean, it does not depend on the value you take. In more general situations, it may depend. So this is our assumption. We assume that the generating function for three connected members has these properties, these analytic properties. And then, well, this is also a bit technical, but I need this in order to state our main result. Now we fix y0, and then x0 is the dominant singularity of this generating function for networks. And d0, these are finite singularities. I mean, the generating function at the singularity is finite. I call it d0. And then our theorem has two parts. If this generating function here has singular type alpha, which is less than 1, then immediately you get that the number of two connected graphs in the family, connected graphs in the family, and arbitrary graphs in the family follow this scheme. This is constantly, this is a minus 5/2 all everywhere. And now this radius of convergence in one case is called r, and in the other case is called rho. Wait a minute, and this rho is less than r. Well, this is consistent because then 1 over rho is greater than 1 over r. So what we are saying is that there are exponentially more connected graphs than two connected graphs. Okay? And the second case, the second situation, it has three cases, but this is the important one. If the singular type is 3/2, then we get systematically minus 7/2, minus 7/2, and minus 7/2. And there are, in some situations, we might have some mixed behavior. So in one case, we have minus 7/2 and then minus 5/2. Or we could even have this. But this is the typical situation. These are more or less anomalous situations that might happen in some particular cases. Now, this singular type is the singular type that comes from the enumeration of maps. There are many kinds of maps. As I said, three connected maps, or cubic maps, or Eulerian maps, or bipartite maps, but all have this universal property that if you look at the dominant singularity and you look at the expansion near the dominant singularity, the exponent is always systematically 3/2. Okay? So whenever we have a three connected family coming from maps, what we should get is this 3/2 exponent. So again, in the planar case, 3 connected graphs are 3 connected maps. The exponent is 3/2, and then we are in this situation because these exceptional situations do not occur. And in the trees, or more generally, instead of trees, I should take forests, which are families of trees, or series parallel graphs, or outer planar graphs, or some related graphs. Then I have this behavior here. Well, some more examples. So this is some more classes of graphs in addition to what I have mentioned. When I say excluded, this means graphs that do not contain, this is excluded minors. So graphs that do not contain this as a minor, or this as a minor, or this as a minor, or this as a minor. So there are 2 parts. This is the tree-like part, and this is the map-like part. These do not fit really into our scheme because they are really below the series parallel. Series parallel is where there is no 3 connected graphs, but these 2 are really very elementary, and the analysis is very simple. So here is a table of these growth constants that I show in the formulas before. Here are the exponents, here are some references, and let me give you some comments. This is the series parallel, excluding K4. We can exclude some more complicated graphs. Why can we do that? Because there are theorems that tell you that if you exclude a given graph, you can determine all the members which are 3 connected. These are due to Wagner and Hallin, who was his student. So they are papers from the 60s. And they tell you that in some cases, if you exclude a certain graph as a minor, then you have a complete description of the elements in the class, and you can get a full list of 3 connected members. For instance, I believe it is in this case you get all wheels, for instance. Or maybe it's in this, no, yeah. I think it's in this case you get all wheels. So once you have all the 3 connected members, you can build the generating function, and then you can use the machinery. You look at the singularity, and in all those cases, the singularity leads to an exponent minus 5/2.
What is the E, the K5 minus E that you're excluding?
Oh, K5 minus E is K5 minus an edge. It doesn't matter which edge because it's symmetrical. Okay. This is the triangular prism. So this is planar. Next row is planar. So planar is the same as embeddable in the sphere. If you ask for graphs which are embeddable in any fixed surface, like the torus of the projective plane, then this exponential term doesn't change, and this is a recent result by Colin McDiarmid. But we really do not know which is the exponent. And one of the reasons is that this Whitney theorem is no longer true. I mean, in the projective plane or in the torus, being 3 connected is not enough for having a unique embedding.
You mean that we do not know rigorously, but we guess?
We can guess because we know the result in the case of maps, and by analogy, we can guess something that will grow with the genus, and we can guess, yes, but we don't know. Well. Now,
mathematicians don't talk about results that are exact but non-rigorous.
I mean, there are some indications. No. I would say that there are some indications that the pattern should be the same as maps, but we are far from having a strong argument and a proof of that. I think we are quite far.
So you're far from betting a good bottle of wine on it.
This is what he means. You think that it could go wrong, or are you fairly sure that it?
Yeah, I would say it's likely, but I don't have a strong I don't have a strong feeling. No, not really. So if you exclude K33, which is a bit more than planar, right? Because planar excluding K33 and K5, then this exponent does not change. This increases a little bit. K33 plus is K33 plus 1 edge, and this is something you can do. But as I said before, if you exclude K5, then we do not know it because the corresponding theorem of graphs not containing K5 as a minor uses something that goes beyond 3 connected components. And we don't have the combinatorial machinery for handling it. So I think this is a very nice open problem. Now let me go to, okay, I have to. So there are two other topics, but they are short both. So the first one is, suppose I want to estimate the number of graphs with n vertices and 2n edges, or 3/2n edges, so with a fixed number of edges. Then there is a technical device which is in this generating function here. You select a suitable value of this variable that will depend on mu with a given analytic relation, so that these become weighted graphs. So every graph has a weight which is y to the k. Okay? And then if you select this y carefully, what happens is that only graphs that have mu n edges get non-negligible weight. So this generative function essentially, there is a local central limit theorem. So there is a window of square root n. But essentially, if you choose the right value, you can get access to the number of graphs with a given number of edges. Now, this is interesting because for planar graphs, what we get is this: the number of planar graphs with n vertices and mu n edges, and mu has to be strictly between 1 and 3. This 3 is natural because a planar graph has at most 3n edges, so you cannot go beyond 3n edges. Then the counting is this. So now this constant will depend on the edge density. This is because of an application of a local limit theorem. So essentially, you have a window with square root n. For series parallel graphs, this exponent is always the same, and now it has to be between 1 and 2, because series parallel graphs have at most 2n edges. But we have found families in which this behavior changes when the number of edges changes. And in particular, if I take this strange family in which the three connected members are triangulations, then there is some specific value that I may call a critical value, probably. And below this density, the exponent is -5/2, and above this exponent is -7/2. We have not found this change of behavior in all, let's say, natural families of graphs, families that are defined in terms of excluded minors or given by some topological conditions. But we have constructed such a family by just trying and using the generating function for planar triangulations, which is again of type 3/2. And the reason is that, let me tell you the reason of that. So in this equation here, the singularities of D can come from two sources. So either they are inherited from the singularities of T, or they are singularities when solving this equation, when solving a branch point. And what happens in this family that for certain values of y, which corresponds to graphs with few edges, there is one source of the singularity that is dominating. And for some values of y which are larger, there is another source. And at some point, these two sources coalesce, and there is a change of behavior, because then one singularity becomes dominant and the other becomes non-dominant.
An implication on the structural difference.
I will go.
Single tree connected
I will go to that. I will go to that in a moment. Okay, because this is at the level of counting. Okay, so at the level of counting, oh, here it is. Okay, I had it here. So the dominant singularity either comes from these or comes from a branch point when solving these. And this is a difference at the level of counting. But I want to give now a difference at the level of random properties. And this is my last topic.
Just a question. For mu equal to mu naught, you can also control this?
Yes. We get an exponent which is of the form, I don't remember if it is now 2/3 or 5/3, but it's not a square root type. You get something that in the denominator there is a 3. Okay. And
it will be 5 that in order to be in between.
Sorry?
I bet the one which is in between.
No, I mean, in this kind of asymptotic combinatorics, you usually get something which is always typically of a square root, right? Maybe the exponent is -3/2 or -1/2 or minus, but it's quite seldom that you get this exponent 3, and this is what we get in the denominator in this critical case. But we have not finished all the details of the computation, so this is why I didn't want to talk about the critical point. Yeah. Now, what about random graphs? For all the classes that I have mentioned, systematically we have that the number of edges is asymptotically distributed following a normal law with mean variance and mean expectation and mean variance. the number of connected components is asymptotically a Poisson law, and the probability of a random graph being connected is some constant precisely defined. It's to the minus the exponent of the parameter of the Poisson law. The largest component is always very large. It's not a linear fraction. It's n minus some constant. So for instance, for planar graphs, the largest component has expectation, which is less than n minus 6. So it really eats up almost everything. But this is not only for planar, for all the families I have investigated. And the difference is in the largest 2 and 3 connected components. The 3 connected components is a bit more technical, so I will just talk about the largest 2 connected components. So this means that I take a connected graph, I look at the different 2 connected components, and I want to know which is the size of the largest one. Why we can analyze this? Well, because we have all the machinery, and the machinery is in this paper. One of the authors is in the Zoom, down there. And the title is longer, but I have shortened. But the important thing is there is random maps and Airy phenomena. What they do here is the following. So they show that the largest 2 connected component in random maps is a different universe. I mean, you count maps according to the number of edges and not to the number of vertices. But again, I mean, the decomposition into 2 connected components has the same sense, the same meaning at the level of 2 connected graphs. It follows an Airy distribution. What is the Airy distribution? I will not give the details. It's related to the Airy function, which is a solution of this differential equation of second order. And okay, so it's a non-symmetric distribution. It's non-symmetric. It's unimodal, but it's not symmetric. And here we have an exponential decay, and here we have a polynomial decay, right? But you can, it's an explicit distribution that it's related to this solution of this differential equation. And now there's something called critical composition schemes. Essentially, this is again this idea that a map is a 2 connected map in which you do substitution, and more or less this kind of a scheme corresponds to something that the authors call a critical composition scheme. Now, what we have done is, because the nice thing, this is a great paper, I recommend you. It's not easy reading, but it's important. And they gave general tools. If you check that your generating function follow some schemes and some singularity patterns, critical composition means essentially you are composing 2 generating functions, 2 analytic functions, and then the first one evaluated at the singularity gives the singularity of the second one. This is what is called critical, right? So if I evaluate, forget about this U, if I evaluate H at the singularity, at its singularity, then I get the singularity of C. Then you can apply these techniques, right? And you show that the size of the largest 2 connected component is linear. I mean, the expected size is linear. So this means that you have a large 2 connected component. Let me, okay, I just need 2 minutes. So, okay, there's no.
Somehow higher there.
Oh, it's higher there.
Higher. On the board, higher.
Okay, thank you. It's just a picture, right? So this is how we should understand a planar graph. Well, I'm saying connected planar graph, but really when you go to arbitrary planar graphs, as I said, I mean, the largest connected component is almost everything. So there is a large 2 connected block that has size linear. And then these are the cut points, but these are smaller. And smaller means that they are of order n to the 2/3. So with high probability, you get a largest 2 connected component which is linear, and there are fluctuations, and you can describe these fluctuations around this expected value using this Airy distribution.
You mean the second largest is n to
No, that's different. I mean, what I'm saying is that you have this Airy distribution. So this is alpha 0n, and this window has width n to the 2/3.
The window for the size of the largest.
Yes. So if you have an asymptotic Gaussian law, So this is in the number of edges. For the number of edges, when I say that this is asymptotically normal with linear mean and variance, is that the number of edges is concentrated around some mu0 n, which in the case of planar graph, this mu0 is 2.2 something, and this width is square root n. So this is a different width.
So the polynomial tail is towards smaller n.
Yes, polynomial is to this end. So here the decay is minus some x alpha. Sorry. And here is exponential decay.
Is there a nice heuristic to understand the asymmetry there?
Sorry?
Is there a nice heuristic to understand the asymmetry?
No, I don't have it. So, Cyril, no. No, I don't have an understanding of the asymmetry of this. But for series parallel graph, the picture is like this, right? So just small bubbles. Well, by the way, this is what happened with trees. So trees, the only two connected components are edges, which are indeed very small. So in the series parallel case, you should expect constant size. And I think this gives at least one structural difference between one family and the other, because, as I said, the other parameters do not change. And I think that's the end of the talk. Thank you.
So the area distribution is in fact the distribution of a stable law. And so is it possible to, for people in probability theory, they would be in love if you can find the sum of random variables which would convert to this limit law. So can you see what could be the random variable?
Not at all. Not at all. Not at all. I cannot see it even in the number of edges, which converges again to the Gaussian law. I mean, I cannot decompose the number of edges, which is a much simpler parameter, into something that somehow would resemble a central limit theorem. Right? So it would be lovely to have this stable law as a limit of something which is more or less independent, but no, I don't think we can have this level of understanding of the situation.
And part of the title that
Sorry?
Airy is not one of the same.
Airy is connected to the stable law of parameter 3/2. It's some variant. I mean, it's not exactly, but it's a variation, and it's. I mean, the characteristic function is essentially given by this, some 2 or some 3, and the characteristic function here is minus x/2.
So maybe we can continue the question and the wine reception. So thank you very much, Marc.